We started P.3 Rational Exponents last time, and if you will remember, we had a couple of things that we did. We looked at how to rewrite radicals in exponential notation, right, with exponents, and how to separate radical notation using those same kind of properties from the exponents we'd seen before. And we did 2 problems, and these were the 2 that we did. So far, so good? All right, all up to date. We're going to take a look at number 3 now. Number 3 looks a little different because it has variables in it. The last 2 did not. And so there's parts of this that look and feel a lot like what we did in section P.2. So taking a look at this one, what do you notice about the inside of the parentheses on this that can be simplified first?
The y and the y-half.
The y on the top, and the y to the 1/2 on the bottom. There's y's in 2 locations, right? So we can use properties of exponents to simplify that at the very beginning. All right, so the x to the 1/2 doesn't change. What property can we use to simplify the fact that we have a y on the top and the y on the bottom? Subtraction of the exponents, very good. So what is the exponent on the y on top? Because it's not really sort of visual. There's a 1 there, right? There's an understood 1 right here. So this is 1 minus a 1/2. And it's all raised to the power 3. I mentioned this last time, I'll mention it again. Make sure that each step is equal to the step that you did before. In other words, even though I'm not going to do anything with the 3 exponent right now, it's still there. It should still be present and accounted for. All right, so taking a look then, I've got x to the 1/2. What is the power on y? It's also 1/2, right? If you had a whole and you take away half of it, you have half left. So this is also 1/2 to the power 3. Now, there are lots of different options that I could do right now, at least a couple different options. So I'm going to show you one of them. One of the options that we can take a look at doing right now is changing this back into exponential, or into radical, notation. So how else could I write x to the 1/2? Square root of x. And the same thing with the y, right? Okay, what does the power 3 tell me that I'm supposed to do to something? Cube it, which would mean to multiply it by itself 3 times. So whether you write all of the x's together or whether you write them xy, 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 either way, you end up with, I don't know why I put the parentheses separate like that at the end. Who knows? But you end up with the square root of x written 3 times and the square root of y written 3 times, right? Yeah. Okay, so take a look at what happens then if you start multiplying things out. What happens if I multiply the square root of x times the square root of x? It's just x. And likewise, if I multiply the square root of y times the square root of y, I get just y. Now, the square roots at the end, however, are still left. That was a terrible y. Let's try again. So I have a square root of x and a square root of y left over. So I can write it like that. That's possible. Certainly fine. You could also write it like this, if you prefer. Either of those would be perfectly acceptable solutions to the system, or to the expression that we started with. Is that okay? Now, I had someone in my earlier class mention, and he was correct as well, what if I wanted to distribute the 3 through right here instead? Right? You distributed the 3 instead of changing it in radical notation. That's perfectly fine. The problem will still simplify and reduce to the same expression. It's just a different way of approaching it. Okay? So if you distribute the 3 through, I want you to take a notice, make note that what will happen is you'll have x to the 3/2. And x to the 3/2 is the same thing as the square root of x cubed, which is the same thing as having the square root of x times x times x. And 2 of these x's can come out, leaving you with x square root of x. So it's just a different way of sort of processing the same information. And of course the y is the same way in that problem. It's not any different. All right, let's take a look at another one. Some numbers in this one. One thing you might notice on this one is that there is a negative. And we get a little anxious when we see negatives underneath radicals. Well, we're going to see negatives underneath radicals sometimes. And in particular, if the radical has an odd index, so remember the index is the number out here in front. If there's an odd number out there in front, Negatives are simply no big deal at all underneath. Because basically what it's asking you is if you had 3 of the same number, you could take its cube root, right? So if you had 2 times 2 times 2, the cube root of that would be 2, because there's 3 2's. Well, if I have 3 negatives, what's the cube root of 3 negatives? So negative, right? So the cube root of a negative is going to be simply another negative. This will be a negative value. Okay, there's no problem with that. It's in essence the equivalent of having here a -1 3 times. Because if I do negative times negative times negative, I get a negative. Okay, so this is happening because this is an odd index. I can separate this out as well with our properties from radicals that we looked at last time. I can write the 125 under the radical, and I can write the cube root of 8 underneath the radical. Now these are particularly friendly ones because they have perfect cube roots. So Amos and I were talking before many of you showed up about when is kind of your calculator useful. That's kind of where we kind of ended on our discussion. Well, it's useful when things work out perfectly with numbers, right? I could put this in my calculator and the calculator is going to be very useful at giving me an answer, even if I can't remember it. But in a little bit, I'm going to do an example with you where it's not going to be useful at all, okay? So does anybody remember what the cube root of 125 is? It's actually 5. And if you didn't know it and you didn't have your calculator, or if the calculator were giving you out these weird decimals, you'd want to do a factor tree. Okay, something like this, 25 times 5, and the 25 is 5 times 5, and you end up with 1, 2, 3 5s, right? So the cube root of 125 is 5. What's the cube root of 8? 2. So on this particular one, you really don't need to show a lot of work, honestly. Some of these are small enough values that you may be able to do them in your head, or maybe you're using your calculator as a resource. That's fine. But it doesn't always prove useful. So taking a look at number 5. Number 5 is going to feel like we're doing something wrong because there's really not a lot to be done at all in this problem. I do want you to realize that we haven't seen as of yet, well, I showed it to you up here in the top right-hand corner, but aside from that, we haven't seen any exponent given to us where it has a numerator that's not 1. Right? This is really the first one that's sort of given to us in this fashion. So as a reminder, first of all, what's going on with the negative? It's on the outside. We've done this like every day now where there's a negative in the problem and we just get to sort of put it out in front and ignore it for the most of the problem. But I have an exponent of 3 over 4. So I have a radical. The 3 is an exponent on the 2, so it's like having 2 cubed. And the 4 is the index for your radical. Okay, that's where the numbers simply go, the notationally where they will be placed to make an equivalent statement. The only thing that can be done in this problem, because there aren't 4 2's underneath to pull out, is to simply simplify what 2 cubed is. And 2 cubed is 8. We actually saw the reverse of that on the last problem. So this problem is done. There simply isn't anything else that we could do to do it differently. Our next problem here, what I'm going to do is give you the sort of directions. They're not written on my slide. I want us to change express. We'll use the word express. In exponential form. So we're going to rewrite it as an exponent form. So just an alternate form of what we were given. Notice there's no simplifying that could be done. If I were told to simplify this one, it would just already be in simplest form, right? There's 2 x's underneath the radical. It's a cube root, so I can't bring them out. I mean, there's just nothing else that can be done. So we're going to practice writing this sort of in reverse notation of what I just did in the last problem, where I started out with exponential form and I wrote it in radicals. Here I'm going to start in radical form and write it as exponentials. So what's going to happen with the 4? It's just going to be on the outside, kind of like those negatives, right? Really not a lot's going to happen with it. How would I rewrite the cube root of x squared in exponential form? X to the 2 over 3. So again, remember the index is the denominator of the fraction, And the power on the variable, in this case itself, is the numerator on the fraction. So our final answer is 4x to the 2/3. All right, a combination problem. That is, it's a combination of the last couple of things we've done in the last couple of examples. This one has the cube root of negative 24a to the 5th. We're going to take it piece by piece. Let's deal with the negative first. What's the cube root of a negative? It's negative, okay? So we start the problem knowing that we're going to have a negative answer. The next value here is 24. Now, technically, we could separate this with properties of exponents. We could write cube root of negative 1, cube root of 24, and cube root of a to the 5th. There's no reason to write this out. I'm just saying we're thinking about it like this. That's why we're doing each of the pieces separately. The 24, however, is not a good example for where your calculator is quite useful. You can put cube root of 24 in your calculator, and it will give you an ugly decimal that will never repeat and never end. That makes the calculator quite useless on this problem. Okay? You can try it. I promise it's still going to be useless. But what we can do with the 24 is we can do a factor tree to figure out how it can simplify. And there's multiple ways to use 24 and factor it. So somebody give me an example. What are two numbers that factor 24 down into? 2 and 12. Okay, so we'll do 2 and 12. You could do 8 and 3. You could do 6 and 4, right? Lots of choices. Your goal is to get all of the ends of the branches to be prime numbers. So 2's prime, 12's not, so we have to keep going. What can 12 factor into? 2 and 6. Be careful not to lose them along the way. There's the prime from 2. And then 6 also is not prime, so we factor it again into 2 and 3. So I have 4 prime factors. They're not all different, but there are 4 of them. I have 2, 2, 3, and 2, right? All right, so if I'm taking a look then at the cube root of 24, it's a cube root. So how many identical factors do I have to have in order to pull it outside of the root? 3, because it's a cube root. Do I have 3 of anything in my prime factorization for 24?
Yes.
I do. What do I have?
2.
2's. So with the negative on the outside will be a 2. And underneath my cube root, there will remain a what?
3.
A 3. All right, the last piece is the a to the 5th. Okay, so there's actually how many a's underneath my radical? 5. How many do I need in order to pull something out? 3. So when I pull something out, I only will pull out one of them because I'm taking out the cube root of a cubed, which is a. How many, so basically I've pulled out a cubed. How many are left? 2 of them, a squared. So there are still 2 a's, or a squared, left underneath my cube root. And there's nothing else at that point that can simplify. It looks really messy, right? The solution's not especially pretty, and that happens sometimes. 8, where I've got a square root of 18, is another really good example where your calculator is quite useless. Every single radical there has numbers only. There's no variables in it. But every single one of them is not a perfect square. So we have to break down each of them, much like I just broke down 24. All right? So let's take a look. We're going to do them one at a time. 18. How will 18 break down? There's more than one option, so give me one option. 9 and 2. That's the one I heard loudest. And then 9 would be 3 and 3. So I have 1, 2, 3 of these. I've got 3 square root of 2. The 3 is repeated. I'm looking for 2 items to be repeated because these are all square roots on this problem, right? Fabulous. Let's do the 50. Break it down. 5 and 10. Okay, so 5's prime, 10's not. 10 breaks down into what? 2 and 5, or 5 and 2, yep. So what will negative square root 50 become? Minus 5 square roots of 2. Okay, moving on down the line, we've got 12. Give me a breakdown for 12. 6 and 2. 6 is not prime, so 3 and 2. So I end up with, is it plus? Yeah, plus, oops, 2 square roots of 3. And then I have the 75 at the end. 5 and what? 5 and 15. Okay, good. And then 5 and 3. So this would be 5 square roots of 3. Now, we've simplified all of the radicals, right? They're all in simplest form. And that allows us to start matching things up to what they can actually be combined with. So do you see anything on that list of those 4 radicals that can be combined? The first 2 and actually the last 2. How do you know if they can be combined? What is it that's making that work? They've got the same, they're like terms because they have the same value underneath the radical. Okay, so the first 2 are alike because they both have radical 2 associated with them, connected to them. So in essence, I really don't have 3 square roots of 2 minus 5 square roots of 2. It's really just 3 minus 5, right? I mean, what is 3 minus 5? Negative 2, and then I associate with it, or multiply it by, the square root of 2 that they both have, the like term part of it. And the same thing happens with the last 2. 2 square roots of 3 minus 5 square roots of 3. What does that give me? Negative 3 square roots of 3. And these 2 cannot be combined in any way, shape, or form because they don't have matching radicals, right? Okay. Just a few more examples in here. 9, especially compared to 8, which was a long problem, is very brief. But I put it in here to bring out the point that you need to be very careful when you see something squared, that you square everything. The tendency here is to forget to square the 3. But the 3 also has the squared applied to it, right? It's grouped inside the parenthesis, kind of like when we've been talking about negatives. So one of 2 options. You can either write this down as 3 squared and then square root of 5 squared, or you could write this as 3 square root 5 times 3 square root 5. But either way you do it, make sure that the 3 gets squared. Okay? So thinking about it in either form, you're going to end up with 3 times 3, which is 9. And square root 5 times square root 5, which is 5. And then 9 times 5, which is 45. Number 10 has different directions. I don't like the idea that what I'm about to do is to simplify things, because it's not. What we're going to have as our answer here in a moment for number 10 is actually more complicated looking than what we're starting with. It doesn't look like it's simplified. But it does have application in other mathematics courses later on. What we're actually going to do is something called rationalizing the denominator. And for our purposes of discussion right now, it simply means we're not going to have any radicals in the denominator when we're done. Okay? So the square roots, if there are any, will only be on top. Okay? So we've got a over the square root of b on this one. Does anybody remember how you manipulate this to get the square root b to not have square root in the denominator? Yeah, you've got to multiply it by itself. So if I multiply by the square root of b on the bottom, however, I got to do it on the top as well. And the reason I'm allowed to do that is because when I multiply by a value over itself, I'm really multiplying by 1. It's the number 1, right? And you multiply by 1, you don't change anything. Now the numerator becomes a square root b. Don't be led to think that the a goes under the radical. It doesn't. It's still out in front. And then on the bottom, square root of b times square root of b is b. And, in fact, I no longer have any radicals in the denominator. But do you see what I mean by saying that this doesn't look any simpler than it started? It actually looks more complicated? Yeah, it does. So what we really did is we rationalized the denominator. Yes, ma'am?
Why on the denominator, why couldn't you have just done it b and then the square root of 1/2?
Like to the 1/2 power, it's still irrational because you've still got the radical involved. Whether it's written as a power 1/2 or it's written in the radical notation, that's what we're trying to eliminate on the problem. Yeah, good question. All right, number 11. Looks kind of funny. Let me actually show you why what I'm about to do is going to work. We've been looking at these alternate forms of changing radicals into exponents and so forth. As we're thinking about this, this actually has another form that we could write it in. We could write the 2a. What does this 4 right here tell you that you could write this as? To the power 1 over 4, right? And then what about the 3 on the outside? To the power 1 over 3. And then you have a property of exponents that says you could multiply the exponents together, right? So the exponential expression that goes along with this is that this is 2a to the 1/12. Right, so if you're asked to put this in exponential form, that's what this would look like. If you're asked to do it in radical form, though, the equivalent would be recognizing that those that 3 and that 4 right there at the beginning can simply be multiplied together. 3 times 4 is 12, and this would be the 12th root of 2a. Okay, so obviously these two are equivalent expressions, right? They're the same, but they're sort of arrived at in a slightly different fashion. Much of this section of material is going to feel like that. If you're comparing your work to someone else's, your work may not look the same, but you arrive at the same answer. That's pretty good indication that both of your works were done in a way that's appropriate. It doesn't always work that way, right? Sometimes we make 2 or 3 mistakes and somehow we still end up with the right answer, but there's a good possibility that there's more than one way to do these particular problems.